Alright, next up we have Eugene Chua from Caltech with Types of Emergence and Physical Coherence.
Hi everyone, so as Charles, I'm going to go ahead and start my talk. So the main aim for today is to sketch the beginnings of a worry, or what I'll call the middle way approach to the problem of time in quantum gravity. I've been working on the issue of emergence of time in canonical quantum gravity specifically, and this worry has been kind of bugging me in the background as I work on like two different things. I'll try to sketch what the general worry is here based on the two things I worked on. It's the worry of what I'll call physical incoherence. The goal, as luck would have it, Sam here and Christina and John Helen wrote a recent book which sketches a similar worry from a metaphysical angle in that chapter 6, I think. So I see my worry here of physical incoherence to augment their worry of metaphysical incoherence. Though we come to different conclusions about what we take away from these worries, I think the worries themselves are very similar. In any case, I want to emphasize that I'm not claiming that all programs in quantum gravity or even in canonical quantum gravity purporting types emergence runs into incoherence, but I do want to say that this is something interesting to investigate and see whether other programs might have something similar hidden within their formalism. So I will illustrate how two prominent proposals, at least two interesting proposals, called the middle way, or which I'll explain in a little bit. The semi-classical and the thermal time programs can run into circularity, and in turn able to motivate future work in this area. So the plan, I'll talk a bit about the background, the problem of time, three general outlooks towards the problem of time, and the problem of metaphysical incoherence at BMT, which I'll short, Baron, Miller, and Helen. How they sort of criticize the metaphysics of the middle way, and I'll talk about my view of physical incoherence for the middle way in two cases, and then I'll conclude some directions for future work and some concluding thoughts. Wrong direction. So let's start with types emergence. So the problem of time schematically, right? While the usual Schrodinger equation you see here describes the time evolution of psi, where psi is the state of matter fields or matter stuff of the system. The Witt equation that one arrives at after quantizing general relativity in the canonical approach, where you impose Hamiltonian constraint, diffeomorphism constraints, and so on, which I won't get into. They do not. You can see here that the time derivative disappears. So the wave function out here is a state not just of matter now, but also three-dimensional spatial slices. So it's a functional of both the metric, the three-dimensional metric, and the matter views on top of the metric. So there's no temporal evolution here for everything. So everything is frozen. It's always called the problem of time, but the more I think about it, the more it feels like the problem of change, but just nothing is changing here, it's just dead. Right? So the state is frozen in time, or like frozen in general. So in this sense, time disappears, assuming that this equation describes the fundamental state of affairs in our world, or universe, or multiverse. One may say that the ontology of quantum gravity appears to be fundamentally timeless. The fundamental ontology does not depend on time or any temporal notions or any like change dynamical notions at all. It seems manifest that our familiar physical systems or at least seems to be evolving in time. And so this tension motivates the problem of recovering time evolution from a fundamentally timeless ontology, which is usually called the problem of time. So in the paper we create calendar, we call this the problem of recovering time from no time. Great title, I think. But in response, I think there have been multiple sort of variations of research programs, decades of research spawning from this problem, many attempts to solve, dissolve them. But there are broadly three sorts of responses I can see towards this problem. So firstly, one can be a time blur, we all call time blur. On this view, time where it exists is fundamentally there, right? Maybe it's hidden in the formalism, you got to find it, the t parameter disappears, but maybe you can recover some other parameter and define dynamical equations with them. So prominent proposals by Greenside and Manavan from the 90s, where they use the total phase of the total wave function to define a parameter they call time. Bohmian quantum gravity does something similar. You bring in the three-metric plus time in the fundamental ontology. Even though the wave function is static, you can have time hidden within it by using the phase of your wave function and conditional wave function and so on. So that's one time blur, which we can talk about that in the Q&A later. The second is what I call time hater. Time doesn't exist fundamentally, and it's just an illusion. We're not going to justify the existence of time in any sense. We're not going to say emergence or whatever. We're just going to say no such thing as time. What we call time is an illusion based on, and we can recover something like dynamics if we took a different perspective. This is something that I think Julian Barber has defended quite a lot in variations of his works from different perspectives. I won't get into that today as well. Finally, today we'll talk about the middle way between love and hate. Right? One accepts that time does not fundamentally exist in the quantum gravitational universe, but we do accept that it exists at some non-fundamental level. But furthermore, it's not just enough to just say that things emerge on top of each other without saying how they emerge. So we're going to say one seeks how to explain through physics time may emerge, and that's like what I call the middle way, like a conjunction of these two claims. So emergence plus an explanation of the emergence from physics. That's what would sort of satisfy physicists. So first, let me talk about the problem of metaphysical incoherence for the middle way, which will, I think, mainly target the first part of that, the middle way, which is the emergence claim. So BMP argues that the middle way runs into the problem of metaphysical incoherence. Standard metaphysical accounts of emergence appear to rely on spatial-temporal properties such as co-location, but these are precisely what do not obtain in a universe without space-time. And since there are no known accounts of emergence that does not employ such spatial-temporal properties, the project of talking about space-time emergence is in itself metaphysically incoherent. Because to talk about emergence, you rely on space-time, but you have no space-time to start with. So what do we mean by emergence here? Very quickly, it's the relationship between fundamental and emergent entities or things or stuff or whatever. There are two general emergence criteria. One is that B is ontologically dependent on A if B emerges from A. And even though B is dependent on A, it's somehow autonomous. So we'll focus more on the first part, which is the question of what ontological dependence is and how do we cache that out. So there are three ways that BNT talks about precisifying ontological dependence. They see it as sort of precisifying the notion of grounding as well. These are three ways in which you can talk about grounding. So one is neurological composition, another is material constitution, and thirdly, functional realization. In a room full of metaphysicians, and I'm not a trained metaphysician, so I'll just kind of quickly skim through it and hope you all understand the general outlines of the idea. So, firstly, before we go down, the way they see it, each option involves specifying emergence in terms of a particular metaphysical relation, and the trouble is that the options are all spatial-temporal or spatial-temporal, or tacitly without the same, and so without space-time, it's unclear that we can make sense of metaphysical emergence in each case. So, first one, neurological composition, very quickly. B depends on A if A neurologically composes B. So A is a part of B, then A composes B. Right? So that's like parts of a plane composing a plane, or parts of a clock composing a clock. Well, they have to arrange in the right way. But the idea seems to be that parthood requires precisification, co-location, and co-location involves location. They consider some options, which I won't get into here, such as Sider's intimacy of parthood notion, Schaffer's neurological harmony notion, and Marcosian's sort of space-time region view. So caching out parts in terms of co-location with its whole, that kind of stuff. And they conclude that the way we usually talk about the concept of neurology or composition to individual parts and whole is not applicable outside of a spatial-temporal context. And the core aspect of the parthood concept and connection to location is lost. Space-time location. So that's the first one. You try and talk about neurology, you end up with a sort of an incoherent view. The second one is persecution, relation we apply when we try to say that something's made out of another. For example, a lump of clay which materially constitutes Thanos, the statue of Thanos. Can we say that time is made up of non-temporal stuff? Essentially, the same problem seems to arise. The standard notion of constitution presupposes a composition. If the statue is constituted by the clay, then the clay and the statue share the same parts. Every part is also part of the statue, but parthood is something to be cached out in terms of location in space-time. So this leads them to conclude that our conceptual understanding of constitution is also all but exhausted by our familiarity with it in everyday cases, all of which seems to involve both location and part sharing of some kind. So again, run into problems there. Finally, a third option, functional realization. More fundamental objects can functionally realize, some less fundamental objects, for example, the mental can be functionally realized by physical. That's the usual, the old claim that pain just is C fibers or something, or like firing on all C fibers and so on. Likewise, in the present context, we might be tempted to say that space-time emerges because it's functionally realized by non-spatial temporal entities. Following Lam-Orchard, maybe a general outline to a functionalist approach would proceed two stages. We try to functionalize the top level, the higher level properties, define a function for functional role for them, and then provide an explanation of how the lower level properties of maybe non-spatial temporal things here can play the role of the higher level functional or space-time role. But there are two sorts of functionalism, and however one catches out this analysis, I think DNT argues that functionalism cannot do the work of catching out space-time emergence from non-spatial temporal entities. As they note, there are broadly two kinds, role and realizer. On the former, pain is identified with the higher order property of being pain is identified with the higher order property of being in pain. So likewise, space-time is the property of being spatial-temporal, which is itself as a role, so a higher order property of being in a state that plays a space-time role. But if the non-spatial temporal thing underneath plays the space-time role, then it does have the property of being spatial-temporal. And this leads to the, instead of a middle way view, to something like a time level view where the fundamental ontology was spatial-temporal all along. A second view would be a realizer view where space-time just is whatever plays the space-time role, but again, this means that the underlying thing in virtue of playing the space-time role has spatial-temporal properties, and this leads to, again, a collapse into some kind of time level view. There's a general worries here of metaphysical incoherence. We've seen how space-time emergence could be metaphysically incoherent based on our current metaphysics on emergence. Standard metaphysics appear to require space-time in their application, and so cannot be applied to non-spatial temporal ontology. So we cannot appear to talk about space-time emergence sensibly at all using our current tools of space-time emergence. So there's a worry that maybe we need to develop new tools, and that they do talk more about it in their book, so I recommend everyone read the book as well. So we can't, the emergence of space-time from no space-time seems to run into rampant circularity here. But what my reply is so much the worse for metaphysics, right? This is working on the middle way. I'm likely to be worried by esoteric concerns about the metaphysics of emergence. I'm not speaking from my own voice, but speaking from their voice. In the remainder of this talk, I want to augment BFT's worry by arguing that the physical analog of their argument from metaphysical incoherence also applies to middle way. And this is a worry of physical incoherence. So it occurs when, for the second part of the middle way, right? They're trying to explain how, via physics, time could emerge from timelessness. The physical tools we employ are implicitly or explicitly justified by temporal notions. And that leads to a physical incoherence because you're just talking about physical tools and asking how do I justify these physical tools using physical considerations, and you run into a circle anyway. So there's a circle from both sides, from the metaphysical side and from the physical side. I see that as like an absolute win for criticizing the theory of like a proposal for space-time emergence. So let's talk about physical incoherence. To sketch this worry, I'll quickly look at two prominent proposals for time's emergence and the middle way in the context of the timeless Wheeler-DeWitt equation. So it will be the semi-classical time program and the thermal time program. I recognize that there are many more proposals for the middle way than these two, but the goal here is not to affirmatively prove or settle the question of physical incoherence of time's emergence in the form of time, but to motivate future work for scrutinizing other programs and assessing whether the same worry might show up elsewhere as well, which will be interesting. And if it doesn't show up, it's also interesting as well. That means that there are programs that are better than others in physics that we can pursue. So let's briefly talk about the semi-classical time program. It's a prominent proposal. It's discussed by Barber in 1993, but also Tiefer in 2004, and also a lot of other people in between and back then. It's what's called the semi-classical time program. Conceptually, the idea is very simple. You start off with a fundamentally timeless ontology. You derive an equation. It looks like this Schrodinger equation. It's functional, but I'll talk about it a bit more. If we only get this though if we assume that we can look at the world in a non-fundamental semi-classical level, so that's some kind of higher level cost-grain picture. And it's cost-grain in terms of two approximations, the von Oppenheimer and the WKB approximation. We can talk more in the Q&A. I don't want to sort of bog down the discussion here, but we can definitely explain it later. But importantly, we also need to assume decoherence in order to get this form. If we don't assume decoherence, in general, the equations will be messy. You're not going to get a very nice thing. You can just label T. You're going to get a whole bunch of different parameters, and they don't look like a nice linear Schrodinger equation. Importantly, though, you can see here there's this HAV, that's the metric, the tree metric, and basically you're evaluating the time at a metric, which means that you are holding fixed a spatial metrics, and you're saying, well, along the metric, how does this other part, the matter fields, change? And then you're defining Schrodinger equation in relation to this sort of clock system, which is the gravitational part, using that to define time for the matter part. So conceptually, to do this, the semi-classical level is where gravity looks non-quantum, so they can sort of separate, effectively factorize gravity from matter. And then gravity plays a role of clock for matter in order to find the notion of semi-classical time for the evolution of matter. Can be cashed out really completely, and therefore satisfies the explanatory desiderata, and for a very long time people were quite satisfied with it. They're like, oh, this looks like makes sense, very nice, and then we can go on to find out the more fundamental sort of quantum gravity theory. Yeah. So there are three crucial steps, like I said. Anderson counts more than 20 approximations in the semi-classical program. Me and Craig, we focus on three, decoherence field and behavior that I mentioned. But there are three crucial steps here, just like sort of lay out the steps. We first assume decoherence to justify a particularly simple form of the wave functional. And then we assume Born-Oppenheimer to justify separating gravity from matter, factorizing them like I said just now. And then we assume the particularity of the WKB, essentially saying that gravity is approximately classical. And then we use that, the WKB on the gravity part to find a time parameter for matter. And then we can use that to define the functional Schrodinger equation. This is highly schematic, and we can talk more about details if you want. So certainly the math checks out if all these steps are justified from start to finish. However, as we have argued elsewhere, these steps all require implicitly or explicitly some kind of background time in order to justify and apply. Without time, we are not justifying to apply these steps. Hence, the program appears to be physically incoherent. And to just give you a taster of how this incoherence shows up, I'm going to talk about decoherence. It suffices to show how just one step fails because all these steps must follow in order for you to get the equation out at the end. So let's talk a bit about decoherence. Well, we talked about it quite a lot in this conference, but everyone's like, everyone in here. Decoherence guarantees that the universe's wave function can be approximated as an eigenstate, not as a position. This is a neutral way of saying that you are pretending to be Everettian, but you don't really want to say you're Everettian, so you just say, well, even you start with a complicated superposition, once you go through the decoherence process, the system is approximately localized or approximately decoherent, and then you can treat the system as an eigenstate of sorts. At least that's what Kiefer says. And this is how we justify using the eigenstate instead of an eigenstate of a gravitational field as opposed to some highly complicated mix superposition. So decoherence, of course, well understood in ordinary quantum mechanics. For instance, you start here with a system in a arbitrary superposition, you entangle with the environment, and you trace it out, you get these cross terms here between different macroscopic states of the environment, but because macroscopic states are approximately orthogonal to each other, over enough time, time shows up here, you run the Schrodinger equation, these cross terms are going to cancel out, eventually you suppress the sort of interference terms, and then you get decoherent states here. But you see here time shows up, right? So it seems like, it seems clear that decoherence presumes temporal evolution. You need Schrodinger equation or even Heisenberg equation to sort of talk about decoherence. Without time, why assume that decoherence will even occur? So some people like Castanino and Laura, they postulate a sort of primitive decoherence in order to sort of address this worry. They say, well, the existence of some kind of evolution, they don't say what, but with such a final diagonal state, which corresponds to the fact that the universe really ends in a classical state. So you just say, well, there's something that drives systems to classical state, but not time, not change, just something, right? We could postulate, based on observational fact, that the quantum physics of the universe is such that there's a tendency towards a classical regime, decoherence from our observation, and therefore use decoherence as a theoretical concept. But this seems kind of ad hoc, because we're just swapping out a conceptual problem of how to get time, the problem of time, with a new problem, which is the problem of decoherence. How do you get decoherence, like primitively? We know how it works. In normal cases, precisely because it's dynamical and we have the Schrodinger equation, we have time evolution. But without that, it seems like it's not explanatory as well. It's ad hoc, and also it's not clear how it works, so it will fail the explanatory desideratum of the middle way. So in trying to explain about how time can be derived from a timeless formalism in a semi-classical approach, using decoherence one runs into a problem of physical incoherence. You're trying to explain Types of Emergence using physics, but our physics is only justified with respect to some kind of time, or like background time, and without time, you don't get time out. So similar worries lurk in other parts of the procedure, like I mentioned just now, as I argued with my paper with Craig, which is here if you're interested. But I'm not going to go into that here. I'm going to talk about a different program instead for graph. So the second program to the problem of time, the double time approach, was pioneered by Connors and Rovelli in 1994. The proposal itself is cashed out in terms of very technical stuff like polynomial algebras, Martin-Stringer, KMS states. But here's how to summarize the conceptual core of the proposal in slightly simpler terms. So starting with a timeless wave function here, you have set 1, I guess it's about the 1 but anyway, you start with a waveless, timeless wave function when h equals 0. Then you say, well, in this spatial, frozen spatial world, like it doesn't have time, but I can still find stuff distributed spatially, just like how Jerome's shirt has like spatial patterns around it. I can sort of find spatial patterns and see if I squint enough, do I find things that look like they're in equilibrium in some sense? Technically, you're saying, can I find states that are in KMS states? And then you get a time parameter from it. But here it's saying, can you find things that look like they're in equilibrium? If you can, then you can find a parameter along which systems are in equilibrium, because things are in equilibrium a long time normally. But now we're saying you're using equilibrium to define time. And that's how you get a thermal time program. We use this parameter then to define other dynamics of other systems, and in short, time emerges from thermodynamics. So MW discusses the standard properties of the equilibrium concept. However, these are all defined in time, like I mentioned. So stationarity, state should not change in time. Stability, state should not change in free energy or change in like some kind of states over time. And passivity, you can't extract energy from this state by applying for any finite amount of time, any local perturbation of the dynamic. So there's a worry here that equilibrium seems to be, by definition, time independent, which means you need to define it with respect to time, without which you can't pick out what equilibrium states are. But if you have to do that, then you run into physical incoherence again, because you have to do a circular reasoning here. So Rovelli proposes in 1993 some kind of intrinsic or timeless notion of equilibrium that does not depend on time for its definition. So for some system S, right, you can find phase space coordinates S prime and S prime prime, so you're trying to partition the system in some way, and assuming weak interaction, so this is a classical case, you're assuming weak interaction between different parts, you can then say that approximately the statistical state factorizes. This is all in the classical case, we're not in the problem time yet. But then Rovelli is going to say that he wants to say that this condition characterizes or defines thermodynamic equilibrium. So ordinarily, you start off with a system in equilibrium, you find this equation and you use this to do other stuff. But now you want to say, well, we use this to define states that are in relative equilibrium with each other. So if two states factorize, then they are relatively in equilibrium with respect to each other for that partition. Then he uses this condition between two subsystems to define a timeless notion of equilibrium. The equilibrium is a situation in which every small but still macroscopic component of the system is in equilibrium with respect to the rest of the system. So every small and macroscopic component. To precify it, you can say, firstly, a system is in equilibrium if and only if every subsystem, every choice of partition, is in relative equilibrium with the rest of the system, for example, S prime and S prime prime, for all choices of S prime and S prime prime, such that they are still macroscopic and one is smaller than the other. Secondly, two systems are in relative equilibrium only if and only if the factorization relation holds between them. So if and only if two systems are approximately statistically independent of each other, then they are in relative equilibrium, then we use that for all choices of S, and then we get that the whole system is in equilibrium regardless of what choice of partition you pick. So Rovelli cites Lipschitz for this definition. However, it doesn't discuss the caveat that comes right after that definition, where they say it should be emphasized once more that this property holds only over not too long intervals of time. Over sufficiently long enough time, the effects of interaction, however weak, even though we assume they are weak, they will ultimately appear. And it's just this relatively weak interaction that leads finally to establishing statistical equilibrium. So that any system out of equilibrium immediately goes back because of the interaction between its subparts. So this Lipschitz is actual physical justification. Relative to certain length scales, interactions vanish, and we can assume that condition, but the condition does not hold for all time. We need to assume some kind of background time scale. So one possible response, however, is to say, well, Lipschitz, they were just doing stuff in the classical context. There's no reason why we need to borrow their physical justification. We just borrow the definition. But you know, it's the case that both parts of Rovelli's proposed definition still encounter conceptual worries anyway. So firstly, defining equilibrium in terms of relative equilibrium for all choices of partitions is too strong. Because the only requirement is that these two systems are one is smaller than the other, and the other is, and they are like sort of macroscopic. But that's not enough. Without further constraints, there are always going to be gerrymandered Maxwell partitions for Maxwell's Riemann partitions of the system into two subsystems. For instance here. just pick sub-regions, collections of subsystems such that they all have very, very, very high kinetic energy, and the other regions have very, very low kinetic energies. I'm not saying you can do it, so I'm not resolving Maxwell's demon or whatever. I'm saying it exists. The partition exists there, so you can do it. You can't do it, but physically it's possible. So if you pick this, then because these are so high in kinetic energy, these regions are going to have really, really high temperature compared to these other parts, and then they're not in equilibrium because one is much higher in temperature than the other. So one replies to say, well, let's roll disconnected set. That's unfair. You're just picking choice regions, right? What if we say that they're both these partitions have to be connected to each within themselves? But this does not exercise the demon either, because only more visceral cases that just raised. Consider a new case where they're connected but still highly gerrymandered, such that you contain only the high momentum or high kinetic energy particles, such that you're dodging all the slow ones. And if you do that, you still end up with a problem, because now relative equilibrium for all choices is not necessary. And secondly, is to worry about whether the factorization condition is sufficient to track whether two subsystems are really in relative equilibrium. So you consider these two, now we have these two partitions, but they are highly insulated, electromagnetically shielded, but they contain air at different temperature. So we can still ascribe a statistical state to these two parts, and they still factorize. We're not going to say that they are like really in equilibrium, because they're not. They are at different temperatures again, and they're not like equilibrating with each other. I don't want to say what equilibrating means. Again, one might be tempted to say connectability is what matters, right? So let's just remove the partition, and then we see what happens. The question now then is, even though it's prima facie sort of plausible that if you remove the connection, also remove the partition, it would be in relative equilibrium. The question here is, what is it about connection per se between the two parts that's supposed to be relevant here thermodynamically? Is it connection per se, or is it something else? Suppose for a second the scenario where the dots will never interact with the, so now we have this partition, they will never interact. But somehow you just imagine in a world where they're still not interacting, but you remove the box. Because they're frozen, right? They're not moving. So even if we remove the barriers, if the world is indeed truly timeless and frozen per the weight equation, it seems like these two are not actually in equilibrium because they're still in different temperatures and they're not connected to each other. So it seems wrong to say they're in thermodynamic equilibrium. And note here that connection is only a means to an end. It seems like it allows for but does not guarantee interaction between the two parts, and that's why they don't come to equilibrium. Once you change the condition to say instead of connecting, that they're interacting, then it's obvious that they spontaneously equilibrate each other. But that's something that happens over time. You need interaction, you need time, you need change. So again, the word problems would not be troubling if we took the condition to hold over time and allow the subsystems to interact, but that's just precisely London's original physical justification, that systems are supposed to be interacting in order for equilibrium to happen, and the definition does not characterize or define equilibrium. It only characterizes it for sufficient enough or like adequate enough timescale for purposes of our modeling. So overall, the system still it has to interact for equilibrium to happen. So we seem to require time to define thermal equilibrium in order to explain time's emergence. And the middle way in the case of thermal time also appears to be physically incoherent. The physical methods that we use to explain time's emergence from timelessness runs into circularity as well. So I have a manuscript here, it needs to be on, but a manuscript here that I work on this, so we can talk about this. You can read this paper as well if you're interested. So to sum up, I sketched the worry of physical incoherence through two proposals. In trying to explain how time emerges from a timeless world, we are trying to use physical tools as physicists, but we end up running into circularity anyway. So it runs into worries analogous to BMT's worry of metaphysical incoherence. However, the analysis here does not explicitly depend on metaphysical concerns per se. It is assessing the proposals from within using the tools of physics, but we still run into the same kind of incoherence here. And I see that these two point to the fact that space-time emergence is really unlike other kinds of emergence, and we need to develop new tools or need to develop new ways of thinking, or perhaps give it up if we are unable to do so. Right. So, yeah. Future work for me. Do other proposals for the middle way addressing the problem of time face similar concerns? For example, loop quantum gravity, it's a coordinate change from canonical quantum gravity. The problem of time is still there, it's hidden slightly, but it's still there. And then the question is there a similar worry there when they try to talk about emergence of time in loop quantum gravity or not? Maybe not, but that's something interesting to see, but I haven't worked on it yet, so I'm interested to talk more about it as well. But secondly, what are the prospects and problems from time level view that I basically hinted at the beginning? For example, Bohmian quantum gravity that Watt sort of has done a lot of work in. Very interesting that it actually solves, if you accept Bohmian quantum gravity, it solves the problem of time, also the measurement problem in the same time, which is pretty nice. But of course, there are like, significant outstanding conceptual problems. For instance, how to extend it to fermions, or how to extend it to how to make it, or how to deal with or cope with the Lorentz non-invariance of the system. And finally, we want to explore other proposals for quantum gravity and claims of space-time emergence in those cases as well. So finally, thank you for your time. Please email me if you have any questions.
And next we have comments from Rick.
I have some slides prepared. Sorry, is there a way to not blur your screen? I can also just grab my laptop too.
Yeah,
Easier.
maybe space settings. I don't think it's just extend.
So much technological settings.
Sorry about that.
No, all good.
So it's supposed to go here.
Yeah, you go stick it there. Ah. Wait, sorry, we're for the notes. Oh, I'm just gonna grab my laptop.
Alright. Sorry about that.
No worries. It's not what it be. Golden. Anyway, thanks so much for sharing this paper. I found it really clearly and succinctly reading, and it was both a thought-provoking and just enjoyable read overall. So, in this paper, Eugene considers the reach of the problem of time for the Hamiltonian approach to quantum gravity. As he notes, our lived experience and familiar physical systems, at least at this level of emergence, both strongly appear to be evolving in time. Eugene gestures toward our old familiar Schrodinger equation to drive home this point. Our models at that level of emergence simply do not run without time. However, given that after quantization, the Wheeler-DeWitt equation suggests a time-independent Hamiltonian, just how can it be that we get, quote, time from no time? If it's the case that is what I hope, our theory of quantum gravity successfully describes reality at its most fundamental level, and if it's the case that quantum gravity really is fundamentally timeless, then, argues Eugene, we must find an adequate story concerning the emergence of time. So Eugene designates three possible approaches to time in quantum gravity, which he calls the time lever, the time hater, and the middle way. To the time lever, time really is there in quantum gravity. It's just the case that it's hidden. Though it vanishes in the Wheeler-DeWitt equation. It is simply the case that there is some other parameter one can, in principle, introduce to recover time in, for instance, our Schrodinger equation. So here's a clarificatory question first. just what does it mean for time to be hidden in these sorts of accounts? So then, to the time hater, time is nothing more than an illusion. On this sort of approach, one might suppose that fundamentally speaking, there is matter in abstract space, but presumably this approach is unpalatable because the ontology is so far removed from our experience. Or at least, we hope that our experience of time is not mere illusion. So finally, on the middle approach, which is the family of approaches that Eugene focuses on, there is no time in our quantum gravitational universe, but nevertheless, time emerges at less fundamental levels. So this middle approach, Eugene argues, involves an explanatory component. Thus, we demand of an adequate account of a story of how plausibly we can get time out of our theory of quantum gravity. So there, Miller and Talent in 2022 argue that quantum gravity is metaphysically incoherent because all of the available middle approaches that they survey, presumably, to emergence rely on spatiotemporal relations, which are precisely what they seek to recover at non-fundamental levels. So here a second question arises. Just how is this assertion about physical incoherence that you raised distinct from BMT's assertion about metaphysical incoherence? Is this a different sort of incoherence? Are we like asserting that there's a bright line or something between these two families of incoherence? So of MBT, Eugene writes, quote, standard metaphysical accounts of emergence appear to rely on spatiotemporal properties such as co-location, but these are precisely what do not obtain yet in a universe without space-time. And there are no known accounts of emergence that do not employ such spatiotemporal properties, so the project is metaphysically incoherent for now, end quote. Of explanatory incoherence, Eugene writes, the explanatory project of the middle way in trying to derive time from timelessness using physics also runs into incoherence. The standard tools of physics implicate time implicitly, if not explicitly. So it would just be very helpful to hear a little bit about the distinction between the hard problem of emergence for quantum gravity versus, for instance, consciousness, and just why this distinction between metaphysical and physical incoherence arises here in a way that it doesn't in the case of consciousness. Okay. So next, Eugene examines two of many possible approaches to time emergence in quantum gravity, semi-classical time and thermal time. So I'll consider the arguments in turn. First, on the semi-classical approach, Eugene writes, quote, given the fundamentally timeless ontology given by the Wheeler-DeWitt equation, time emerges in the non-fundamental semi-classical level, end quote. Eugene suggests that on this approach, quote, gravity plays the role of the clock for matter in order to define the notion of semi-classical time for the evolution of matter, end quote. So Chua and Callender in 2021 argue that in order for this approach to succeed, there are three necessary conditions. We have to assume decoherence, we have to assume the Born-Oppenheimer approximation, and we assume the applicability of the WKB approximation. But unfortunately for the semi-classicalist, it's not obvious just how to make sense of quantum decoherence in a fundamentally timeless world. So as Eugene notes, the first assumption demands that we be justified in adopting the eigenstate eigenvalue link, at least as an approximation. So for those unfamiliar, this entails that for some property A of a system, there's a self-adjoint operator A hat with eigenstates A sub I, bracket notation, and corresponding eigenvalues A sub I. It is necessary then that these decoherent eigenstates are sufficiently non-interacting. So notably, David Wallace is a harsh critic of the eigenstate eigenvalue link. He argues that it's the mere invention of philosophers and that it ought not be taken seriously as it plays no role in empirical inquiry. It doesn't even appear in textbooks more advanced than introductory undergraduate texts. But it's not clear to me how we assign properties to entities without it. So I'm left wondering, on behalf of the semi-classicalist, just how good must this approximation be in order to make their argument go? Do they require the eigenstate eigenvalue link? Also, just we can put an asterisk there. I have personal investment in this question, so if you want to skip the response to that question, we'll talk later. So it may be that this is a moot point since decoherence appears to require time anyway, and as Eugene emphasizes, it's incoherent to presuppose time if one's goal is to show from whence it emerges. So the second approach Eugene considers is thermal time. In particular, he closely examines Carlo Rovelli's 1993 attempt to reconstruct an account of thermodynamic equilibrium that does not require time. So a question here, if any given definition of equilibrium is timeless, it's not obvious to me how we go about disentangling this account from time. Is it not the case that the property of being timeless means constant in time? It seems like any such approach will fail. It's kind of doomed. which I think you agree. If you have any further clarifications there, that would be helpful. So it seems that both the semi-classical approach and the thermal approach are doomed to fail, as both tacitly rely on time to get going. But finally, if you'll ask me to just permit like a quite naive question that's been with me for like some number of years, if we want any dynamical change whatsoever in our universe, shouldn't there be dynamical change at the most fundamental level? And how is this possible without presuming time, period? So your paper has made me worry that the middle approach is simply untenable unless we posit some like higher order time-like parameter, which it sounds like maybe one of the people you discussed tries to do. And it was very ad hoc. But that seems to defeat the purpose of like the mission to get time from no time. This would of course be like a lowercase time from an uppercase t time or something. Though Eugene notes that taking out all middle approaches would be a Herculean task, I struggle to see how any approach like in the middle could really succeed. But maybe I've been too easily discouraged. Either way, Eugene's done a terrific job motivating the claim that the path toward an adequate account of time emergence in the Hamiltonian account of quantum gravity is a tall order. So thanks again, Eugene, for sharing this awesome paper.
Brief response.
All right, I'll be very brief. I'll try. So what does it mean for time to be hidden on the time overview? Like a quick, like will be something like you have a wave function and you have your assuming you can write it in this form. Then you just take this part and you just like do like a grad S kind of thing, or like something like Bohmian mechanics. Then you get time from this. Like there's a dynamical equation defined in terms of this term. So even though this thing doesn't change, including the S, but the grad S can sort of drive time evolution because you have a hidden, I'm not going to write something like that, but you know, like you have a time derivative that is defined in terms of grad S plus some other terms. But that's like the rough already version. So even though the wave function is not changing, the phase, there's a phase, as long as the phase is not real, if it's like an imaginary phase, so there's some constraints there. If it's an imaginary phase, then you get to do stuff like that, and you get a Bohmian sort of approach out of it. I think other approaches also do something similar. They don't think themselves as Bohmian, they just say you use a phase directly and just define time in terms of that. So but there are ways to do it, even though the wave function is not changing, there are ways to get change out if you added more stuff into it. Yeah. But those people are not going to say time emerges, they're just saying, well, fundamentally it was there, we just had to redefine it in terms of some other equation. So you're not like running into troubles or emerges. So second assertion, actually it's a good question. I wanted to talk more with Sam about this as well. I'm not sure if it's like this thing, I think it's this thing in terms of framing definitely. I'm just doing it from within physics, but the worries are very similar, and it might be that it's just more specific on instantiations of the more general metaphysical world there. In which case, you'll drive a project where you just take this metaphysical account, go around and try to instantiate it and see whether the project fails or not. Might not fail, might fail, that'll be interesting to see either way. But I think it's not I think it's this thing in that sense that it's framing different and language are different. We're talking about different concepts or theories. They have a theory of metaphysical emergence where they're talking more about physical theories. But I'm not sure if the spirit of it is like different, so there's something to talk about there. Thirdly, how good must the approximations be? They have to be good with respect to, at least in classical cases, with respect to time. So very quickly, usually you can like sort of write the approximation lead you to write something like this, and then you sort of factorize it in terms of this. You have your H and your matter fields, and then this is just H. So this like you're factorizing these, but you're assuming that this is much more massive than the other, and therefore justifying the factorization. But what justifies factorization because of mass? It seems like it's something to do with change and how things change with respect to each other, fast or slow, that allows you to say this is approximately unchanging with respect to this, and that's why this is the bottom line of approximation basically. And then you furthermore assume this is a special kind of wave function in terms of WKT wave function, which is approximately classical wave function. But those also require spatially slow change in potential and so on. But you can see how a lot of stuff sneak in there when you, even if it's like explicitly, formally spatial, stuff comes in there. So it has to be really good. I think it has to be so good that it doesn't appeal to time, unlike in all the standard use cases of the it's not impossible, which is why I kind of, it's not impossible, but it seems like any standard conception of it runs into trouble. Similar to how standard conceptions on emergence runs into trouble. Maybe we can come up with a new theory in the future, but right now we are at our limits. So on thermal time, if any given definition of time, yeah. So I guess timeless is something I added. He calls it intrinsic, but so intrinsic is not explicitly timeless, but it is in terms of purely spatial considerations. Just eyeball a box of stuff, and then you just try to partition them, and you're not saying they're changing over time. Just saying defining a statistical state at that time, they factorize it, so on. But then of course it runs into worries that I mentioned just now. And finally, will there not be dynamical change at the most fundamental level? I think that I personally like something like the time level, I love time, I guess. So if I want any dynamical changes, I do think you have some kind of change at the fundamental level. It might not be time, though. It might be something like causation or something more fundamental, but there has to be some kind of dynamical notion going on there, at least in my view. If you wanted something higher up as well. So that's just my take. Thanks.
All right, we've got 15 minutes for questions, so I'll ask people to speak.
Thanks, Eugene, as a great. I see where you're coming from. So I'm going to mention a few things you didn't talk about. There's no like the way you mentioned the work by Sam and Christy Miller. It's interesting that it's kind of an Australian tradition in a way, because the Australian tradition was a lot more in the mood of going elitist about time and space-time, and not really into the mood of the middle tradition. So he also has another paper by David Mitchell, Christy Miller, like this one. There are also the papers by Sam as well. But I guess in other cycles, like if you look at the work in the quantum gravity, people were a lot more sympathetic to what we call the middle way. And attempt at solving the problem of empirical coherence, this kind of problem of physical coherence in real sense, was kind of mingled with the problem of metaphysical coherence, I think. Just to say that there was this thing happening there, and also personally I've been advocating for composition, trying to show that we can have a form of non-spatial temporal composition within the work. And I think I managed to make it respectable for Sam, because we wrote a paper called Composing Spacetime, criticizing his former work going against using composition. So just to say that there is more room for this view.
Great. Yeah, so definitely I want to talk to you more about the other options that I have. So I think the way I see this paper is like, I already have the physical incoherence arguments there, and I saw that it was, well, there's a similar interesting framing between, alignment between my arguments and Sam's, maybe not former arguments, and so I thought it was interesting to connect, and I definitely, it will be interesting if the metaphysics works out, but still the physics side of it has no way of catching out. And it suggests future research programs that might try to catch it on more concretely. Maybe in loop quantum gravity it works already, then that's fine. That's the one thing I haven't really studied yet, so that's something I want to look into as well. But I don't think these two programs run into very severe physical problems, even if the sort of metaphysics works out. But it will be interesting, and I want to talk more about it. Yeah, thank you.
Sebastian.
Yeah, thanks so much, Eugene. I enjoyed it and the comments. So I think my question is a worry that you raised at some point. Just maybe some clarification on that. Like, in some of these projects, like the equilibrium one, right, where you kind of appeal to some notions coming from, say, statistical mechanics or other things, it's just maybe a bit strange that if you think that the most fundamental, I guess, equation or law is the timeless one, right? Then you go to other these theories, right, like statistical mechanics, or to get tools there to see how is it that time emerges.
Yeah.
But in a way, it kind of looks strange because we know that all those theories have dynamical evolution there, right? And it kind of seems to me like it's going the opposite direction. Like, let's find a tool in these other theories to extract time from there. But these are supposedly to be emergent theories already with time and all of that. But so there is a worry, but I don't know if there is any other way out except starting with these dynamical systems instead of trying to go from the other direction.
From the top down.
Yeah, or something.
Yeah, no, I agree. But I think it's a bit subtle because, like, actual formulation like how already it's like in terms of C-star algebras, right? So you have your state, right? Just like statistical state, just if you can find states at a time, right? And those states satisfy like the KMS condition. I don't write down the KMS condition, but if it satisfies the KMS condition, it just a parameter comes for free from that state at that time that you can identify as a one parameter strongly continuous unitary group. And then it looks like you get it for free, so you don't have to worry about the more dynamic. So even if you have one state at a time, you have a state, right? That state gives you a parameter for free. So it looks on the face of it that the math just brings with it a parameter that you can just apply. But I think just worry like when you're allowed to apply the formalism, and when are you allowed to interpret the unitary group as a time evolution unitary operator as opposed to some general symmetry operator. And that's a big worry, and that's why I work on it more in my paper. But yeah, I think there's a problem here, because this doesn't always align. Like, any state can have any state at all has a free parameter like this. But my cup of coffee doesn't have, it's not in equilibrium, even though it has a time along which it could have been in equilibrium. So that's a worry there. So, but that's more subtle, and that's why I didn't want to bring it up here. But yeah, that's a good question. Thanks.
Right.
Yeah. So I'm just wondering what you see as the analogy and disanalogy between the quantum gravity middle way and what just a special relativity block universe kind of story, especially when you have your kind of no change from no change formulation. Because if you just think that, block universe, you might say, look, there's no change here, it's just a 4D block, it is what it is. And then it seems like you might have the same set of options. You can either do the hidden time, inversion time, or illusion time. Yeah, so anyway, do you think that is an analogy? Do you think the middle way is more successful in that case, or so what's the difference?
Yeah, I think they are analogous in some sense, but I guess the 4D block has time in it, right? It's 3 plus 1, right? So we know that there's a time, and it's well defined in terms of like GR and so on. Where
Do you think it's just not that hidden is the answer?
Yeah, it's
so
not
really
that hidden. This is like really hidden,
yeah.
And this is hidden in like some kind of 3-dimensional, or like some kind of spatial slice, and you should find the right time. And the problem which I didn't raise, my fault, but in the equation, like, you can't deparameterize, there's no good reason to deparameterize any one of the parameters as time, just by eyeballing whatever the state of the equation is. We don't have a full equation, but whatever the equation is, try to eyeball it, you're not going to find you can't deparameterize and find the time. So it's a bit more tricky than like GR, where you know there's time somewhere that you just got to find it, like, oh, it's there. But here it's like you don't even know where to start. Because you started with time, you quantize, and then that time parameter disappears. So now you don't know where to start. Yeah. So that's a worry. Thanks.
Other questions? Other question. I guess I'm just sort of on the physical incoherence side of things. I'm wondering, I think some time lovers will see time anywhere, right? And so I'm curious to know what kinds of physical tools we could have to use if we really wanted to try and get rid of time and have anything that looks like dynamics that kind of make sense of physics. And so I guess there are two cases that I'm interested in. One of them in the decoherence case, where the notions like stability, because one of the questions was like, when does decoherence occur? And it's like, well, when the things are highly unstable or something like that. And there might be modal ways to cache that out that aren't temporal. And in the thermal case, it looked like one of the issues that you had with the notion of equilibrium is this notion of interaction. Right? And if there is a way to sort of understand interaction that's not temporal, you might be able to recover the sort of thermal time hypothesis. But I'm just wondering if the time level is going to be like, there'll be interactions this timing thing, and like even notions of stability of these timing things. And so is it ever going to be the case that you'll be satisfied that we've got a period of time, or all these physical things just too tiny to ever have anything like the project?
Yeah, that's a good question. Definitely, as you were saying, I was like, yeah, that's my thought, right? And then you said that's what I would say. I do see time everywhere, and maybe that's just my lenses are broken or something, but I just see dynamical. I feel like if the top level is dynamical, the bottom level has to be dynamical in some way. It may not be time, for instance, it could be like causation or something that drives change more fundamentally, but something must be driving change for there to be change overall. So like if you have decoherence, you talk about decoherence, you have this frozen slice, like for example, frozen 3-dimensional spatial slice, and you say, well, if I find decoherence here, then I find time. But if the decoherence is a kind of some kind of evolution, then there's change right there, and fundamentally there is change in the world. Then it's not emergent anymore. It's like some kind of change going on at the fundamental level. It's just that maybe it doesn't look like the time window at the top. But that's not quite the worry. The worry is that there's no change at all, and now you're trying to find change from a changeless world. Yeah. So that's my worry. But maybe I just
yeah. I mean, I guess there's something weird going on, right? Where it's almost like you can't get rid of time conceptually, right? There's always some like Kantian thing happening where it's like time is this a priori lens that we look at, and like, you know, I give you change and I say, well, it's change, it's not temporal change. And you're like, no, but it's change, it's got to be time, right? And so there's something sort of weird happening here, I think. Like, is there some like background assumption here that time is like an a priori constraint on the way that we think about everything? And if that's the case, then like none of these projects are ever going to work, right? Yeah. These sorts of time from no time project.
Yeah. I mean, I did start off like having these like sort of like I just like looked at it and I see that all the tools we are using are justified in this temporal context, and there's no story for how we're supposed to think about them without these temporal sort of assumptions or justifications, and that's what worries me. But I'm open to like a thoroughly changeless like sort of way of looking at it. If there's a formalism that could. But the good question is what satisfies me, and I'm not sure. So right now nothing satisfies me, but I'm not sure exactly why. But but I think my arguments are fairly convincing for myself, and hopefully some of you as well. Yeah, I don't want to say I'm a Kantian. I mentioned Kant at the summer school on gravity. Everyone looked at me like what? So but I do think I have some leanings there in the sense of I can see it. I feel like I need to have it somewhere in order to get all this stuff out about time. It might be that I'm just wrong, but right now that's just my perception.
Just to follow up, I think this supplement what you just said. You know, in philosophy and just in everyday experience, time is profoundly puzzling. It's profoundly mysterious. So it's interesting. I'm struck how in the physics it turns out to be mysterious too.
Yeah, mysterious yet utterly necessary. I think is essential.
Yeah, and that's the felt push towards just being Kantian. You know, you've got to start with it. Otherwise, we can't make sense of anything.
Yeah, yeah, I sympathize with that.
Good. A little bit of time if someone wants to sneak in a little while. Yep, sure.
Yeah, perhaps this is naive, and we talked a bit about it last night, but understanding kind of like static dynamics, or the dynamics without, this kind of changes in these views without that just being something temporal or time-like. I know you used the patterns on the shirt analogy. Could you just say a little bit more about that? Because I still can't get my head around what that's supposed to be. Like I can see the equations and like, oh yeah, there's no time term, but
yeah, I'm trying to draw like that. I'm just like channeling Craig here, but he likes to draw shirts. So like, I mean, assuming this is like gravity or whatever, you know, like it's check, right? It's a shirt. But then you have other stuff here, your wave function. But then you can say, well, at this point, the wave function is here, and at this point, it's like here, right? And you just say this is like key, but so you're like changing, this is changing with respect to this part, how fixed. So that's how you get like, it's kind of similar to how you get time from a block universe almost. Yeah, so there's no, yeah, this is how the way we should be seeing it. It's like it's a cloud in that sense.
stacking layers of states.
Yeah, yeah, okay. With respect to one state, like a variation in that one state, how does other states change? That's like the gist.
Okay, we've got 1 minute, Stephen.
A very quick question. Can you say something more about the empirical evidence for the Wiener-Levittic equation?
The empirical evidence? Do you have empirical evidence? I mean, maybe we do for like quantum gravity or string theory. I don't know. Do we? I don't think so. Yeah. We have whatever evidence we have in QFT, but that's why we're kind of all just grasping at straws, trying to find the right quantum gravity theory.
I mean that equation comes out because it's like use the standard canonical
Yeah.
quantization techniques things elsewhere, you use it here, you get that thing.
Yeah,
I
exactly.
know all that. The
Yeah.
question is just why we should take it metaphysically seriously
Yeah.
and talk about time and so forth.
I mean,
yeah.
we have evidence for generativity, we have evidence for quantum mechanics, and we have evidence of the two go well together.
Yeah.
So we have evidence to take seriously attempts to put them together.
Yeah. Just put it this way, like we have as much reason to think about this as we have for everything. So, right?
And on that note, let's